And welcome back to week 3 of hashtag remote rocks. Um, as you can see, I got a little bored at home, so I decided to take a trip down to Disney World. Um, it's a little empty, not sure why. These guys here, not practicing social distancing correctly. Hopefully, you are at home. But hopefully you guys are getting the hang of things as we're getting the ball rolling here. I know that a lot of you guys have been doing some great work and getting a lot of your stuff done. Seems like you're managing your time pretty well. There's others of you that might need to find a schedule that works best for you. But always remember that we are here for you. Really, we're just trying to get you into the best situation possible. So if you guys need any help, please reach out. If you feel like you're a little overloaded with work from all your other classes and all of our classes, please reach out to us. Let us know. We can always adjust. And hey, again, we're here for you. We're here to help you. But on my way down to Florida, I made sure to pick up some riddles here. So let's go ahead and start with our 3 riddles. Let's start with this guy. So, if the wind blows only from the north, where must I be on planet Earth? Answers in 3, 2, 1. You're on the South Pole, because you're only facing north. All right, a little wordplay here. I start going and end up doing, finish everything and conclude nothing. What am I? And answers in 3, 2, 1. You are the letter G. Think about that. Spell them out. And last one. I'm a 5-letter word, yet it sounds strange to say. 6 still remains when you take 2 letters away. Answer in 3, 2, 1. 60. Take 2 letters away, then you end up with 6. Ha! Gotcha. All right. Anyways, now that we're on week 3, hopefully you've been able to take care of your stuff for week 1 and 2. Just make sure you're trying to keep up with things. Again, if you are falling behind and you need a little extra help there, just let us know. We can lighten the load a little bit. But if you're good with week 1 and week 2, then we can jump into week 3. Okay, we're still on circles, still talking about circles. We're just adding on to it. So again, if you are struggling with those first 2 weeks, make sure you understand those before we move on. But if you feel like you are ready to go, let's go ahead and hop to it. So let's pull this guy up. And again, we are week 3 here. And what are we looking at? So our standards for this week. On our circles, we want to determine and apply the relationships between tangents and circles. Okay, so new word here, tangents. Now, I say new word, but we've actually talked about that word in a previous context. But we'll see how does that apply to circles here. And then in our second video for this week, we'll look at determining and applying the relationships between chords, tangents, secants, and arcs. So another new word there, secants. Okay, so hopefully by the end of these 2 videos, you will understand what those words are. Now, first word, okay, starting with some more vocabulary here, tangent. Okay, now if you recall our tangent back in our trigonometry, if you remember that stuff, that was if we had a right triangle, our tangent of this angle was our opposite over our adjacent. Okay. Now, in this context, we're not necessarily dealing with our right triangles, but here, a tangent is a line or a segment that intersects a circle or a curve in exactly 1 point. So we're just looking at a single point and does not contain any points in the interior of the circle. So it just touches the circle, it doesn't go inside the circle. So if you look at these 2 examples here, we have a tangent here and a tangent here. If you notice, they are just touching the outside of a circle at 1 single point. So it intersects at 1 point. Okay, and that point is what we call the point of tangency. So it's the point at which a tangent intersects a circle, and there's only one. Again, if it intersects twice, then it's no longer a tangent. We'll take a look at that in the next video. Now, if you're wondering, why are we using this word tangent? Well, I thought tangent was right triangles. A little side note here. If you take a look here, and you could look this up, or if you are very curious of why this works, if you look, we have right triangles here, and it actually ties right into, and there's a strong connection between the tangents we're talking about and the tangents that we dealt with in our right triangles. Okay, that's more of a pre-calculus idea, but we could definitely have a conversation about that. Okay, now if we have multiple circles, okay, we could have what we call a common tangent. That's a line or a segment that is tangent to two circles in the same plane. So we have a line or a segment that's tangent to two circles at the same time. So if you look at these examples, all of these guys, okay, they touch both of the circles one time. Okay, and you could actually see up here that these two circles, they're tangent to each other. They touch each other at one single point there. Okay. So just some extra vocab there. We don't deal too much with what we call common tangents, but just something to think about. Now, why are we talking about tangents? Okay, tangents, I would actually say, are very important. A very important concept when we talk about circles. We deal with a lot of tangents when we talk about physics. So if we're thinking a roller coaster, we have a bunch of curves and circles in this roller coaster, and the forces that are acting upon your roller coaster are actually tangent to those curves. So dealing a lot with in our roller coasters, if you think about road layouts, okay, this is our intersection of 33, 161, and 270. Okay, nice new intersection, but you see a bunch of curves. Well, when civil engineers are laying out these curves and these roadways, they have to connect these different curves using tangents. So if you think about this curve here, okay, terrible color, sorry. If you think about this curve, okay, well then you have a tangent roadway to that curve. And that's just how they connect these roads. Additionally, we live in Dublin. How many roundabouts do we have? Well, you have a circle, right? And then you have a bunch of tangents to that circle. Okay. So we see a bunch of tangents out in the real world. So that's why we want to know stuff about them in order to use them. Okay. So that being said, in order to use these tangents, we have to know, okay, what's special about them. Okay, so we have 4 or 5 different theorems that we can talk about. The first one here, it says, if a line is tangent to a circle, then it is perpendicular to a radius drawn to the point of tangency. So what that tells us, if I have a tangent and we tell you, okay, this line is tangent to the circle, if we draw in this radius, I automatically know that we have a right angle. Okay, and that's a given. So if I have any other tangent here, let's say I have, come on, make that a line. Never mind. Okay, let's say that's tangent. Well, then if I draw on a radius, then I automatically know that's a right angle. Okay, so it will help us to solve a bunch of problems, even if it doesn't just blatantly tell us it's a right angle. Okay, now, if I reverse that, the same is true. So if a line is perpendicular to a radius at a point on the circle, then it is a tangent to that circle. Okay, so what that tells us here is, if I have a radius PC in line M, if I measure that, or I calculate and I can see, okay, that's 90 degrees, that's a right angle, well then I know that this is a tangent. Okay, that only touches this circle one time. Okay, and that's actually a way that we could prove that it's a tangent. Okay, if we measure this and it comes out to be, let's say, 85 degrees, okay, well, that would then force this line to go through the circle. It would intersect twice, making it no longer a tangent. So it has to be a 90-degree angle. Okay, all right. So that being said, let's go ahead and solve two problems here. Okay, so based off of that first theorem, it says BC is tangent to circle A at point C. I want to determine the value of x. Well, if I look at this picture, okay, if it says BC is tangent to this circle, well, AC is a radius, so I automatically know that's a right angle, which then gives us a right triangle, which if I have a right triangle, we know that we have the ability to use Pythagorean theorem. So a squared plus b squared equals c squared, because if I'm dealing with sides of a right triangle, we know that's always true. Okay, so again, we saw this in last week's videos, but here, let's think about how we plug this in. So the only thing that we need to make sure of, this 17, that's our hypotenuse, so that has to go into the c. So 17 squared. Okay, the other two are interchangeable, so I could put a 14 squared here, and then I could say x squared. That's what we're solving for. Okay, so now if I want to solve this, I have 14 squared. I have 196 plus x squared equals 17 squared, which is 289. Okay, now if I solve this, I'm going to subtract my 196 from both sides. So I have x squared is equal to 93. And then if I want to solve for x, remember you take the square root. So x is approximately 9.64. Okay. All right. If you have any questions on that, please, again, make sure you reach out, ask about that. But that's all solely based off of that being a right triangle. Okay. All right. So that second theorem, we're going to use that here is to determine if BC is tangent to circle A. Well, again, that told us, well, if I want to check if this is a tangent, I need to check, is that a right angle? Okay. Or in this case, is this triangle a right triangle? Well, if you recall from previous units, in order to check that, I can plug these numbers into the Pythagorean theorem, and if it works out, well, then I know it's a right triangle. Now, I need to check, do we have all three sides? Well, I have this 9, right? I have this 12, but I don't actually have this whole side. I only have this piece here, this 6. Okay, so I'm missing this piece here. Okay, well, that's a radius, isn't it? Well, I have a radius here, so we know that that guy is, in fact, 9. Okay, which then tells me this whole thing is 15. So if you remember your Pythagorean triples, 9, 12, 15, if I simplify those, that comes out to be a 3, 4, 5 right triangle. So I know right off the bat, yes, that's true. If you do not remember that, you could always plug this in. You could say 9 squared plus 12 squared equals 15 squared. Okay, so 9 squared, I have 81. 12 squared, I have 144. And then 15 squared, I have 225. Okay, if I add these up, I get 225 equals 225. That checks out. So that is indeed, yes, a tangent. Okay, so that's how you would check that guy. All right, so those are our first two theorems. Okay, theorem number 3 about our tangents. Okay, it says if two segments from the same exterior point are tangent to a circle, then they are in fact congruent. Okay, so what that's saying in this picture, I have two tangents. So XA, now that extends all the way, that's a ray. But in this case, we're just looking at XA and then XB. Now they're both tangent to the same circle. They both start at the same point at X. So this theorem says that these two are congruent. Well, why would that be the case? Okay, well, if I think about this, if I draw in this, what we call auxiliary line, that gives us two triangles. Okay, and in fact, since those first two theorems, they told us, well, these are right triangles. Now, in this circle, AC and BC are radii, so I know those are congruent, and XC is reflexive, so that's congruent. So then by HL, we know these two triangles are congruent, hypotenuse, leg. Takes us all the way back to standard D. So if I know that these two triangles are congruent, what else do I know? Well, I know all of their corresponding parts are congruent. Remember that CPCTC. Man, bringing it all back. Okay, so that tells us that these two tangents, these lengths, are congruent to each other. So that's what this guy tells us. Okay, so I can use that to solve some problems here. So it says a photographer wants to take a picture of a fountain. She positions herself at point A. AB and AC are tangent to the fountain. So I want to know how long is AB. Okay, well, we see two tangents. We know right off the bat they are congruent to each other. So if they're congruent, we know I could set both of them equal to each other. Right, and now I just need to solve for x. I'm going to subtract 5x from both sides. So 2x, I'm going to add 9 to both sides. So I end up with 14. And then x divided by 2 gives us 7. Now, keep in mind, I'm looking for the length of AB. So I have to take this, I have to plug it in. Right, so AB, plug that in. 7 times 7 is 49. Minus 9 gives us 40. And I believe the problem here actually said it was in feet. Okay. So as simple as that, we know if I have two tangents, set them equal to each other, boom, you are done. Okay. All right. Now, when I have those two tangents and they intersect outside the circle at x, okay, that actually creates an angle here. Okay, and we give that angle a fancy name. We call that a circumscribed angle. Remember, we had an inscribed angle. Inscribed. Okay, that was your angle that was on the inside here. Okay, this is a circumscribed angle, an angle that is on the outside. So it's a angle on the exterior of a circle with sides that are tangent to your circle. So angle x in this case. Now our theorem here says our circumscribed angle and its associated central angle are supplementary. Okay, so what that tells us here is angle x and angle C, those are going to be supplementary, which means they add up to 180 degrees. Now, why is that the case? Again, if we go back to our congruent triangles, if we split this up, we know these guys are right triangles. We've already proven they're congruent, right? Well, we know that this angle here and this angle here, right, congruent to those angles because they're congruent. Well, we know that this angle plus this angle, they have to add up to 90 because it's a right triangle. And then that also means that this angle here and this angle here have to add up to 90. 90 plus 90 gives us 180. There's a proof. Okay. Another proof that we can talk about going back to standard E, if you recall our quadrilaterals. Okay. This is a four-sided figure, quadrilateral. I have a 90 and a 90. Okay, the sum of these angles has to add up to 360 degrees. Well, if I take away the 90 and 90, that takes away 180. So what does that leave us with? That leaves us with 180 degrees to split between these two angles. Okay, so what that tells us is the measure of angle X plus the measure of angle C is 180 degrees. And that will always be the case. Okay, so let's take that and apply to a problem here. So it says determine the measure of angle X and angle C. Well, I have 10x minus 3, 19x plus 9. So if I know they're not congruent, okay, and just by this picture, you can kind of see, well, they're not going to be exactly the same. Okay, they're supplementary, which means they add up to 180 degrees. So let's go ahead and 10x minus 3, add that 19x plus 9, and set it equal to 180. Okay, now I need to combine my like terms, so I have 29x, I have plus 6 equals 180. If I subtract my 6, then I end up with 174, and then I need to divide by 29, and if I divide each side by 29, I end up with 6. Okay. Now, again, here I want to know what are the actual angles, so I need to take this 6 and plug it in to both of these guys. Okay, so the measure of angle X here, if I take 6 times 10, that gives me 60 minus 3, so that's 57 degrees. And the measure of angle C, okay, I could plug it in, or I could just take away from 180. Let's go ahead and plug it in. I have 19 times 6, which gives me 114, plus 9 gives me 123 degrees. Add those up, they add up to 180, so it checks out. Okay. All right. Now, one last thing here. If I take those circumscribed angles and I draw multiple of them where they all connect, that actually gives us a circumscribed polygon. Okay, so we have several different examples here. Okay, but the definition of your circumscribed polygon, it has vertices outside the circle and all the sides are tangent to that circle. So it basically says, well, I'm fitting this circle inside this polygon and it's touching each of the sides. Okay. If we had time, we could go through and we could actually construct these circles and these polygons or these triangles. I think that's something that we're just going to leave off for now. Okay. But example here is triangle JKL is circumscribed about circle Q. So I want to find the perimeter of triangle JKL. Okay, nice and easy, because going back to that one of those first couple of theorems here, okay, what it told us is if I have two tangents, okay, they're congruent to each other. So if I think about this guy and this guy, because they're tangent at this point, well, we know that those are congruent to each other. So JM is 14, JP is also 14. Okay, same thing up here, MK, NK, if they're 1, 7, the other is 7. Okay, and then last but not least, if I have NL and PL, those are congruent, so that's 11 and 11. So if I want to find the perimeter here, well, then I just take all of the sides, I add them up, and I end up with 64. Okay, we don't know the units, so let's just tack on units. And there's your answer there. Okay, just based off of your theorems. All right, so let's go ahead and sum up what we just figured out here. So first theorem, first and second theorem really. If a line is tangent to a circle, then it is perpendicular to a radius drawn to the point of tangency. And for example here, if I have a tangent and a radius, we know that those are perpendicular. Okay. Theorem number 2 here, if two segments from the same exterior point are tangent to a circle, then they are congruent. So again, here, if I had two tangents, they intersect out here, well, then I know that they are congruent to each other. And last but not least, a circumscribed angle and its associated central angle are supplementary. Okay, so what that told us is if I have a similar picture with that circumscribed angle and that central angle, those guys are supplementary to each other. They add up to 180 degrees. Okay? If you know those 3 facts, I think you are squared away, you are ready to go. You could solve a multitude of different problems. Okay? So that being said, make sure that you're understanding these, that you're following along with those examples. Okay? If any of those examples didn't make any sense to you, then please, again, reach out. Ask us about them and we will help you out and clarify and just make sure you got those down. Okay? But if you are good, you can go on to some practice or you can hop on to our next video. We're adding in our last segment. If you recall that last word, our secants. Okay? Again, hope you're doing well. Hope you're staying safe. Hope you're keeping up with your work, but not overloading yourself. Okay? We will see you when we see you.